All right, today I need to start off by going over the exceptions. So if you could take a look at the front of 65 briefly. On the front of 65, the only exceptions that we have are for the elements hydrogen and oxygen. Those are the only elements that have exceptions, hydrogen and oxygen. And you can read what it says here, but I don't think it's necessary to memorize those words because I'm going to teach you what I think is a better way to deal with the exceptions. So with that, just know hydrogen and oxygen have exceptions. Okay, so how is that going to help us? Guys, when we are assigning oxidation numbers, yesterday for problems like number 1 where we knew the hydrogen, we knew the chlorine, and I said, okay, we're done. Now we're just going to have to check. We always have to check our math. And in this case, plus 1 minus 1, that adds up to 0. Yay, that was good. There wasn't a problem. That's why that's not an exception. Or likewise on number 11, I did check the math because I wanted to show you that it added up to -1 for hydroxide, right? The -2 for the oxygen and the +1 for the hydrogen. And that was good. That wasn't an exception because it added up to -1 and it should have. But now for the exceptions. If you add up what you know and it does not add up to what it should, that's an exception. So put your pencil down because I'm going to write wrong stuff first as I figure out that I have an exception. So let me look first here at number 9, right? Looking here at number 9. If I assigned these as I had learned them yesterday, I should have said that oxygen is -2. And then that fluorine, I can use my halogen rule because it was the last element in the formula. And I can say that that's -1. Guys, without doing any math here, is there any universe where adding those up is going to add up to 0? No, they're both negative. Adding two negative numbers would never give me 0. So guess what? This is an exception because it doesn't add up to what it's supposed to. So in that case, once I know, hey, it didn't add up right, how do I handle it? Guys, what are the only two elements that have exceptions? Oxygen and hydrogen. So you know what I'm going to do? I'm going to leave the fluorine alone and I'm going to make oxygen X. I don't have to memorize any specific rule for oxygen. I just have to know that it's an exception and that's the one I'm going to change. And now I solve for it. Now I can say that stays in X, the fluorides are -2 because there are 2 of them, and adding them together should equal 0. And what is that going to make X in this case? X would have to be a +2. And so those would be my answers, +2 and -1. Bam, I just did an exception without memorizing anything else besides I know oxygen and hydrogen are exceptions, and I checked my math. That's how I figured out that this one had an exception in it. And that's how it will work for all of the exceptions. If I go down here to number 12, right? Again, since you guys won't catch it at first, I'm going to write it down, but if you're in pen, then you're going to have to scratch stuff out. But if I had assigned this as I had learned them, barium is in group 2, and we know everything in group 2 is +2. We know oxygen is -2, and on the surface that might look like good stuff there. Except there was only 1 barium and there were 2 oxygens. Guys, that's +2 and -4. That does not add up to 0. That's how I know that this is an exception. And what are the only 2 elements with exceptions? Hydrogen and oxygen. So guess what? Oxygen's the one that I change. Leave the barium alone, make oxygen X. So then this becomes a 2X and I solve for X. Adding those together equals 0. X is going to have to be a -1, right? So that's how you can handle all of the exceptions. There's only one time that it will not serve you well, and that is specifically with number 13. Number 13 is the only exception that has both elements with exceptions. So if you plugged in +1 and -2, this doesn't add up to 0, but then the issue becomes, well, which one do you change? Well, I'm hoping that you guys might actually recognize this chemical formula. Anybody happen to know what H2O2 is? Something you can buy at the store. It is hydrogen peroxide. So if you didn't know that was hydrogen peroxide, hey, welcome to hydrogen peroxide. H2O2 is hydrogen peroxide. And in hydrogen peroxide, the exception is the oxygen. That's the only time reading the rules on the front might have helped because it does say that peroxide's oxygen is -1. But Other than that, just hydrogen peroxide, oxygen is the exception. The peroxides are the exceptions. So in this case, I would leave the hydrogen as a +1. Oxygen I would put in as X. And so when I solved for X, I'd have a +2 for the 2 hydrogens. I'd have a 2X for the 2 oxygens. And making that add up to 0 then, that means my X should be a -1. So that is the only exception that's tricky because it has both elements with exceptions. But the rest of them, it's only either hydrogen or oxygen is in it that you can change. So looking at number 22, Li, group 1, that should be +1. Hydrogen should be +1. +1, +1. Does that ever add up to 0? No, we're going to leave the lithium as the +1 though. Hydrogen is your X. Hydrogen has exceptions, lithium does not. Guys, I shouldn't even have to write down X. What does hydrogen have to be here? A -1, because there's one of each. So if lithium's +1, hydrogen's got to be -1. So that was number 22. And then lastly, number 53. Just I'll show you the math that it doesn't work out. If I put in calcium as +2 and I put in hydrogen as +1, again, any universe where 2 positives can add up to 0? Nope, not going to happen. And so between calcium and hydrogen, it's hydrogen that is the exception. So we'll leave the +2 for the 1 calcium, but it's 2X for the hydrogen. So setting that up, 2X plus 2 equals 0. X would be a -1. So that's how I handle the exceptions, guys. Just checking your math. If it adds up to what it should, cool, there were no problems. But if it doesn't, there's an exception. And the only 2 elements with exception, hydrogen and oxygen, solve for them. You just got to remember H2O2 hydrogen peroxide, it's the oxygen that's the exception to solve for. Okay. So with that, let's check answers to the whole entirety of this worksheet. Starting with 1 through, make sure you're going side to side, 1 through 20. And then I'll move on. And I don't have any work to make it simple. Those are the answers. Raise your hand if you're not good through number 20. A couple more seconds. Scrolling down, I'm going to stay with 21 to 45, 21 to 45 coming up. And did everybody catch 24? I know not all of you did. That's one you guys tend to miss. Raise your hand if you're not good through 35. Only 35. Everybody good through 35? Okay. Then let's get the rest of it up. 36 to the end. Okay. All right, so what kinds of questions do we have? Questions? Yes. 21. All right, coming back up here. 21. So did you put CL as -1? Can't do that. That's the sometimes rule. CL is only -1 when it is the last element in the formula. So I had to put the K as +1, the O is -2, and then CL was X that you had to solve for. So that also, I noticed that on the bottom. That's where I saw it. I noticed it more frequently on these two. Guys, you can't put the CL and the BR as -1 because they're not the last element in the formula. The only time I could do that was the first one, and also ones like number 20 and 25. There was okay because the CL and the BR are the last elements in the formula. There they are a -1. Okay. All right, other questions? Yes. 39. 39. All right, so I'm going to kind of draw this out. You had MnSO4, right? And you only know oxygen. So I kind of think of this as a box sometimes. This was a compound made with a manganese ion and a sulfate ion. And everything in the box has to add up to 0. So sulfate has a -2 charge. If the sulfate is -2, what does the manganese have to be to make everything in the box add up to 0? +2. So that's how I figure out that the manganese is +2. Then I can separate, ignore this now, and say sulfur is X, oxygen is -2, and then sulfur X. Right? But I had to use my concepts of polyatomic ions and how to write ionic compound, right, formulas to figure out that the manganese was +2. Yes?
Why is ammonia considered an ionic compound?
Ammonia?
Yeah.
It's not. It's molecular. Yeah, it's actually, you've done dot structures for it. It's a trigonal pyramidal shape. Now, ammonium is a polyatomic ion, but not ammonia. All right, yes? 54. So once again, if I think of my box here, PbNO3 has 1 lead and 2 nitrate ions, and each nitrate has a -1 charge. So that's how I figure out that the lead has my +2 charge on it. And then in that case, I would have distributed and written N2O6, where the lead would have been +2, the oxygen -2, and then I would have solved for nitrogen, right? But you got to use the whole polyatomic ion to kind of figure out what the lead's charge is before you separate it into nitrogen and oxygen. Do you want me to keep going there, or is that good? Okay. Manny, is that a hand?
Yeah.
Yeah.
What do you do with the charge in 55?
What do you do with the charge in 55? You set it equal to the charge.
Okay.
So when I set it up, it was X plus a -6 equals a -2. That's why it's +4 and not +6. Because it's got to equal -2, not 0. All right. Other questions? All right. Then with that, we're going to be adding some notes to the front of this. And then we got a worksheet that will be due tomorrow. And guys, I'm trying to make a push to get it all done today. So that means tomorrow you'll get a whole chance to work in class and hopefully not have homework going into the weekend. Right? But here we go. Make sure we're adding things to the front here. All right, first thing that I want to add is up top here, and that is in a redox reaction, the number of electrons lost by the substance that is oxidized must be equal to the number of electrons gained by the substance reduced. Guys, it's conservation of electrons. I know they don't really have mass, but the electrons still aren't magically appearing or disappearing. So we're going to keep that in mind as we get to some of our questions today, that yes, Leo the lion says grr, losing electrons oxidized, gaining electrons reduced, and it's got to be an equal amount. Whatever gets lost goes going directly to the thing that's gaining it. All right, so step one, we want to be able to identify if a reaction is a redox reaction. So how are we going to do that? The most specific way to do it is that we're going to check oxidation numbers. Because in a redox reaction, the oxidation numbers of two and exactly two elements change. So remember, you've got a reaction that has reactants and products, and conservation of mass, if you got a hydrogen on the reactant side, there's going to be a hydrogen on the product side. And if you assign oxidation numbers to all of the elements on both the reactants and the product side, in a redox reaction, what you will find is that for two of those elements, their oxidation number on the reactant side will be different than their oxidation number on the product side, indicating that they have gained or lost electrons. And guys, we said this is peanut butter and jelly. It's got to be two elements or none. Can't be three, can't be one. You messed up if that happens. If something lost electrons, something else had to gain electrons, that's always two elements. Okay. So on your test, you're going to be asked, hey, which of the following is a redox or which of the following is not a redox reaction? This is one way to do it. Assign oxidation numbers to everything in all four reactions. It's kind of annoying. So let me give you maybe a shortcut. There are some quick things that you can do to at least narrow down your choices. And that is, there are certain types of reactions that will always be a redox reaction. It might require you to review some of your Unit 9 chemical reaction stuff, because a single replacement reaction is always a redox reaction. That was the home wrecker, right? You had the happy compound couple, and then you had this single element that was going to come break up that compound, right, to make a new compound, and then you had the new single element. That was your single replacement reaction. Also, any combustion reaction, which if you remember, the most simple definition was reacting with oxygen, anything that had plus O2 on the reactant side. Most combustions, though, did use hydrocarbons, those like CH4, C2H6, C3H8, reacting with oxygen to form carbon dioxide and water. So if you can look at your four answer choices, that could either help you immediately identify, like this one has to be a redox, or it could help you eliminate if they don't want the redox ones. Conversely, there is a type of reaction that will never be a redox reaction. And that is your double replacement. Your double replacement reactions will never be redox reactions. Guys, that's why we always say the charges stay the same on both sides. That was your home wrecker, right? Put together the outsides, put together the insides, the wife swap, right? So, yes, you can assign oxidation numbers to everything in all four equations. That'll get you your answer, but you could definitely make it quicker by eliminating some of your answer choices from remembering this. Mrs. Tate, what about synthesis and decomposition? Those are, it depends. Sometimes they are, sometimes they aren't. So I can't say 100% one way or the other. So what are some common examples then of redox reactions? Rusting. The rusting of iron, photosynthesis, and cellular respiration are all examples of redox reactions. I think your test read also talks about like bioluminescence, perhaps. I don't know that equation offhand. All right, so that's how we know it's a redox reaction. Once we have a redox reaction, the next step would be to identify what has been oxidized, what has been reduced, what is the oxidizing agent, what is the reducing agent, and you can tell the total number of electrons that have been gained or lost. So, how we're going to do that. The 4 steps here kind of get you to identifying the 4 first things. What's oxidized, what's reduced, reducing agent, oxidizing agent. And guys, it all begins with step 1. You gotta assign oxidation numbers to everything, to every element and every reactant and every product. That's why it's so important that you guys can assign your oxidation numbers. But once you've done that, you are gonna focus in on the 2 elements whose oxidation number changed from the reactant side to the product side. So some of your equations might have 3 or 4 elements in it. Don't worry about the 3rd and 4th one. Just focus on the 2 whose numbers are different on the reactant and the product side. Those are your 2 answers to every question. So how do you know which one's which? Well, it tells you here with number 3. It says, remember Leo the lion says, Grr, gaining electrons actually means your oxidation number will become more negative because electrons are negative. So if I gain negative things, I'm moving towards the negative side of a number line. But here is a kind of quicker way that we can write this, and that is the substance that is reduced, its oxidation number is reduced. It's going to the negative side of a number line. So that could be from +6 to +3. That could be from +3 to 0, 0 to -2, -2 to -4. Anytime you're going that direction on a number line, that's going to be, for you guys this way, I guess, right, reduced. Now I focus on that. If the oxidation number is reduced, you're the substance reduced. Guys, oxidation will be the opposite. Which way will the number be going? Not getting reduced, but going up, right? Oxidation number goes up for your substance oxidized. Your oxidation number goes down for your substance reduced. So that's how you know it's oxidized and reduced. And then lastly, we have our agents. We have things called reducing agents and oxidizing agents. So to help explain these, I'm going to use a little analogy here. Does anybody know what a travel agent does?
They put together fees and stuff, I think.
Put together fees? What does a travel agent do?
Kind of like set up your hotel and like plan travel.
They help you travel. Do they travel themselves? No, but they help you travel, right? Okay, so remember that with agents. Agents are helping. So I'm going to use Parker here as my demonstration here. And Parker's got these paper clips that we're going to say are electrons. All right, and so Parker's going to come to me. And he's going to be like, could you help me get oxidized? Would you be my oxidizing agent? And if he wants to get oxidized, what is it that he wants to do with his electrons? Because Leo, if he wants to get oxidized, he wants to lose electrons. So he comes to me, Mrs. Tate, will you please help me get oxidized? Will you be my oxidizing agent? Okay, sure, no problem. Let me help you. I will help you lose electrons. Give them all. I want them all. All right. So I've helped him get oxidized, correct? I was his oxidizing agent. But guys, what just happened to me?
You got more.
I gained electrons. So what else am I? If I gained electrons, I got reduced. Guys, I'm doing double duty. By helping him oxidize, I also got reduced in the process. I can't only do one. And so it overlaps. It overlaps that one of your agents will also be something that was oxidized or reduced. Because we could think of it as the other way around. I could have gone to him and said, let me just leave that there to start with. I could have said, oh, will you please help me get reduced? Please? Will you help me get reduced? Yeah. Reduce, please. Help. Okay, so he helped me get reduced, so he's my reducing agent. But then what happened to him? He just lost electrons, so he was oxidized. You see, we're doing double duty. It's just from the point of view that you're looking at, right? I gained them, but I also helped him lose them. That's how I gained them, correct? Okay, so at the end of the day, what I tell students is, guys, for the agents, you just got to mix up the words. The reducing agent is whatever was oxidized. The oxidizing agent is whatever was reduced. So your reducing agent can also be reduced. Like, they got to be different words. All right, the substance oxidized is the reducing agent. The substance reduced is the oxidizing agent. And on these notes, I'm going to use RA and OA to abbreviate those so I don't have to write out the full names. All right, so I'm going to do 2 examples that we're going to try to fit on here. I'm going to do one example up here and another one down there. So bear with me here. All right. Example 1. We're going to do rusting, the equation for rusting. So we have 4 atoms of iron plus 3 molecules of oxygen yield 2 formula units of Fe2O3. So that is the equation for rusting. And we are going to identify what has been oxidized, what has been reduced, my oxidizing agent, and my reducing agent. Spoiler alert, we only have 2 answers for all 4 questions. Next thing, your answers can only be reactants. Products are never the answers to these questions, only reactants. Reactants are the things that gain or lose the electrons, not the products. That's what you have at the end.
So is oxidation like taking away oxygen or something?
No, I mean, it got named that way because oxygen was involved with it a lot, but it's not, you don't have to have oxygen for oxidation. It's not about, like, when things combined with oxygen, they tend to oxidize, right?
So it's just giving away electrons.
Oxidation is losing electrons, yes. Okay, let's go through and do this. Guys, step 1, assigning oxidation numbers. So you remember on your worksheet yesterday where everything was in squares? So don't write these squares, but you can think of this as these are like 3 different squares on your worksheet from yesterday that you're treating each of them separately to assign oxidation numbers. Then, unlike your squares yesterday, these have coefficients. Any of our squares yesterday have coefficients? No. So do we need to worry about coefficients? The answer is no. They're there because it's a balanced equation, but the presence of coefficients does not change or affect how you assign oxidation numbers. So really, I'm assigning oxidation numbers to these. Okay. So let's start off with this one. What's the oxidation number for Fe? Guys, what I encourage you to do on these equations is always look for your uncombined elements first, because this is 0, and some of you will pick up on that, but there will be a lot of you who want to put -2 here, and you cannot. That is not -2. That is an uncombined element, and the uncombined element is 0. You'll get better at this, but O2, Cl2, Br2, don't just start putting down -2s and -1s. There's 0. They are uncombined elements. But here now we do have a compound. So now we can say that this oxygen is -2. So what would the iron have to be? Yeah, if I think of my math here, that's a 6 and that's a 2x. So this is going to be a +3. All right, so that was step 1, assign the numbers. Then I focus in on the elements whose oxidation numbers are changing. Guys, pretty simple on this one. There's only 2 elements. So we have the iron who went from 0 to +3. We have the oxygen who went from 0 to -2. So now I'm ready to answer my question. Who was reduced?
Oxygen.
Guys, I just look for the number that went down. And I always start with reduced because that's the one I go to in my head first. To be reduced, your oxidation number is reduced. So oxygen went from 0 down to -2. So that means O2, 0 was reduced. I sometimes put the 0 or sometimes not. Don't let that throw you off. But what's important is I didn't put O2 minus. O2 minus is your product. Products don't gain or lose anything. Okay. All right, so then what was oxidized? Guys, it's got to be the iron. But the iron went up, right? The one that goes up, 0 to +3, that's oxidized. So here, Fe0. Not Fe3 plus, because that's a product. Products don't lose electrons. All right, so then for my agents, remember for my agents, I'm just pairing up the opposite words. So who is my oxidizing agent? The oxygen, because the substance reduced is also your oxidizing agent. And who's my reducing agent? Fe. Fe0, because the substance oxidized is also your reducing agent. They're doing double duty there. All right, so the last question will be how many electrons were gained or lost? And I'm just going to put number of electrons here. To answer this question, you only need to pick one of your elements that changed. It won't matter which one, because we know if we pick the one oxidized, however number of electrons we said it was lost, that would be equal to whichever one was reduced, however many it gained. They have to be the same number. So if I've done it right, it doesn't matter which one I pick, the one that was oxidized or the one that was reduced. So I'm going to pick the iron because it was the first one in the equation. And I need to know two things. The first thing I need to know is by how much did the oxidation number change? In this case, it went from 0 to +3. So that means this iron lost how many electrons? If it went from 0 to +3, how many electrons would that be? Not a trick question. 3. Guys, it's 3. If it went from 0 to +3, it lost 3 electrons. And because it was oxidized, right, the number went up. That's why I say it lost 3 electrons. So I know that iron lost 3 electrons. But guys, those numbers are for one atom only. One atom lost 3 electrons. In that balanced equation, how many iron atoms are there? Guys, there's 4. Conservation of mass, we started with 4 on the reactant side. We ended with 4 on the product side. So each atom of iron lost 3 electrons, but there were 4 atoms in the equation. And again, this is all for iron, which means if all 4 atoms each lost 3 electrons, total how many electrons is that? 12 electrons. You're just counting the number of electrons. Now, I'm not going to do it for the oxygen, but it works. I would have said each oxygen gained 2 electrons, going 0 to -2, and there were 6 oxygens, 3 times 2. So each of the 6 oxygen atoms gained 2 electrons. 6 times 2 is 12. Right? All right. Last example here. Fit it down here at the bottom. Example 2. C6H12O6 plus 6O2 yields 6CO2 plus 6H2O. Anybody know what that equation is? Not photosynthesis. Somebody just say titration? It's respiration. Yeah, it's respiration. The photosynthesis makes the glucose. Respiration breaks it down. Okay, so same 5 questions. Guys, step 1 is always assigning oxidation numbers. So remember my tip. Look for all the uncombined elements first. We only have one of them. That's your O2. Everything else is compounds. So now we can go through the whole group 1 is +1, group 2 +2, all of that fun stuff. So can I say that my hydrogens are +1, my oxygens are -2, and then I don't have a rule for carbons, so I'm going to have to solve for my carbons. Over with the carbon dioxide, can we agree that if we have -2 oxygens, that the carbon's going to have to be +4? And then I am going to write down a little bit of work here for the glucose, because this is going to be 6x. We're going to have a +12 with the hydrogens, and oh look, a -12 with the oxygens. What is that going to make x? X is going to be 0. That doesn't happen often, and in fact, it's more complicated than what I'm showing you, but that's fine. We're going to put the 0 there. So that's step 1. Assign oxidation numbers. Step 2, figure out the 2 elements that are changing. So there's only 3 elements. Let's focus on which one didn't change. Which element's oxidation number never changed? And that would be the hydrogen. Mrs. Tate, what about the oxygen? Well, the deal with the oxygen is some of it changed. Guys, as long as some of it changes, it counts as one that changed. They don't all have to change. So the hydrogen is none of my answers. What I'm focusing on is I've got this carbon and this oxygen changed. And I don't know why I picked the water one, but I did. That's fine. Actually, I could pick this one because at least then it would be the same number. But those are the ones that changed. When I say same number, I mean 12 oxygens each. All right, and so now that I focused on those, I can answer my questions. I always start with who was reduced. Oxygen. It went from 0 down to -2. So notice I do write the subscripts of my uncombined elements. I did that in the last one. I put the O2 with the 0. If he was reduced, then which agent is the oxygen? Oxygen was reduced. It is which agent? The oxidizing agent. The substance reduced is the oxidizing agent. All right, so then who was oxidized? Who was oxidized? The carbon, right? The carbon went up from 0 to +4. Notice that I'm not going to put the subscript. I don't put subscripts for things in compounds. I only put the subscripts for the uncombined elements over here. That's not going to be a huge sticking point. The key thing is I didn't put C+4 because C+4 is a product. Products aren't your answers. And if it was oxidized, which agent is it? Reducing agent, right? The substance oxidized is your reducing agent. So lastly, for the number of electrons transferred, guys, don't mess with the oxygen. Some of them changed, some of them didn't. Like, that's a weird thing. You can do it, but you got to think more. Stick with the carbon. The carbon's all changed. So let's focus on the carbon. Carbon was oxidized. That means it lost electrons. How many electrons did it lose if it went from 0 to +4? It lost 4 electrons, going 0 to +4. But then how many atoms of carbon are in this equation? 6. So total number of electrons lost by the carbon, 24 electrons. That would be also exactly how many the oxygens are gaining if you did the math. All right, so we've got one more thing left to cover, and then we'll be done. Let's take a look at the back of number 66. The back of number 66. All right, redox reactions, oxidation reduction. Guys, sometimes these get pretty complicated. So what we have found is that it is often nice to just focus on one thing at a time. Focus on just the oxidation or focus on just the reduction. And so if you're focusing on just one half of the redox reaction, we call these half reactions. So down here you see these are half reactions where only oxidation or reduction is occurring. We don't need to really know more about why we do this, just that's a half reaction. It only is about oxidation or reduction. One of the things that we're going to have to do is identify if these half reactions are oxidation or reduction half reactions. Guys, it's about whether or not the oxidation number goes up or down. So all we will have to do is look at the oxidation number to see if it went up, oxidation, or if it went down, reduction. So we're going to do examples here, but that's all I need to look for. And then lastly, we are going to balance these half reactions. But don't panic, they're not super crazy. There's only 2 steps. Step 1 is you try to balance your atoms by adding coefficients. The only time you ever need to do this is if one of your elements has a subscript on it. So I'd like you to look at this table right now And I want to figure out what is the first question in this table where I would have to balance atoms using a coefficient. So take a second to look down here. Don't say anything out loud, think to yourself. Where's the first question that you would have to balance your atoms using a coefficient? Think. All right, on the count of 3, we're going to use our fingers. Put up your fingers for which question we think needs to be balanced with the coefficient. 1, 2, 3. And it should be question 3. Do you guys see how there's a subscript 2 here? We're going to need to balance that by putting a coefficient 2 right there. But the 2 in front of it, guys, nobody had a subscript. So there's one of each. We're fine. They have different oxidation numbers, but there's only one of each. So that's always step 1. And guys, you don't actually have to do that for a lot of these. There's only a handful that you have to balance the atoms. The more important part is you got to balance the charge. An interesting thing about half reactions is they include electrons. So you need to make sure that the charges on the reactant side all add up and the charges on the product side all add up and that they're the same. So the way we're going to do this is we're going to figure out the difference in our oxidation numbers. That's going to tell us how many electrons we're going to use. And then we are always going to put those electrons on the side that's more positive because all electrons can do is bring a charge down since they're negative. So here we go. I'm going to do some examples with you here. So I look at number 1. First thing I check, do I need to balance with the coefficient? Nope, I don't because there's one of each. So then I go to balance my charge with my electrons. So I look at these oxidation numbers, 0 plus 1. That is a difference of 1 electron, correct? So I'm going to put 1 electron in my equation, and I'm going to put it on the side that is more positive, which is my product side. So my balanced equation, half reaction, Au0 yields Au plus an electron. That's it. Because now the plus 1 of the Au plus and the negative from the electron, that adds up to 0, and that equals a 0 on the other side. And then my oxidation number, it went from 0 up to plus 1. So is that oxidation or reduction? If your oxidation number goes up, that's oxidation. Remember, to be reduced, your oxidation number would be reduced. It would go down. So that's it. That's all I have to do there. Let's look at number 2. I always check, do I need to balance atoms? And I don't because there's no subscripts. Then I look to balance my charge. The difference between those oxidation numbers plus 2 and 0 would be 2. So that means I need to add 2 electrons. But I need to add 2 electrons to the side that is more positive, which now is the reactant side. So we're going to have 2 electrons plus Fe2 plus yields Fe0. And can we see how the negative 2 from the 2 electrons and the positive 2 from the Fe2 plus, that now adds up to equal to 0 on the other side? They're both the same charge. Lastly, my number went from plus 2 down to 0. So this is which type of half reaction? It is a reduction half reaction. All right, last one here. I've already balanced my atoms, right? We had a subscript 2, so I needed a coefficient 2. So now I focus on balancing my charge. This is a negative 1, this is a 0. So that's a difference of 1 electron. But guys, I also need to account for my number of atoms, right? 1 atom would have lost 1 electron, but I have 2 atoms. So I'm going to need 2 electrons. When you have a coefficient 2, you are going to have to double your electrons. So that means I'm going to use 2 electrons. I'm still going to put them on the more positive side, which is my product side. And here's my final equation. 2I minus yields I20 plus 2 electrons. Do you guys see how the 0 and the negative 2 on the right side will equal the negative 2 on the left side? That's why I needed 2 electrons. If I only had 1 electron, they wouldn't be equal because this coefficient 2 applies to that charge as well. All right, and then my number, it went from negative 1 up to 0. So which type of half reaction? oxidation. Okay, so that was getting you going. There's only 9 more left here. You do not need to worry about this bottom half right now. Just through number 12 is what you're looking at on this side. Let's turn around and look at the other side. Okay. At the top, you're reviewing just assigning oxidation numbers. It just is only asking for one number for one element, like it would on a multiple choice test, but that sometimes means you'll need to do work to figure out that one element. Okay. In the middle here, just reviewing changes in oxidation numbers, like for number 17, if the number changed from +1 to -1, can we agree that that would be 2 electrons going from +1 to -1? But does that mean that those electrons were gained or lost? If you went to the negative side, that means you gained negative electrons, right? Going from +1 to -1, that means your number's going down, you're gaining them. And then the last 4 down here are like the 2 examples we did on 65 with the resting and the respiration. Tell me what was oxidized, reduced, the agents, and how many electrons were gained or lost. Guys, remember for 25, it's the change in your oxidation number times the number of atoms of that element. It's the change in the oxidation number times the number of atoms of that element. That's how you get that number of electrons gained or lost. So I understand it was a tight day today. Please ask me questions, send me pictures. I would like to help, but that means all tomorrow is pretty much just going to be more review and practice. I'd rather you have the extra day of just practicing than not have enough time to get everything done tomorrow. Okay?